NASA has just detected a massive dark region on the Sun, and it is not what it seems. This is a coronal hole, a place where solar wind escapes at high speed, sending streams of charged particles across space, some of it heading toward Earth. But what exactly is this hole? How does it form? And what does it really mean for our planet? This video follows the journey from the far edge of the Sun's influence, through its outer atmosphere, and down into the hidden layers beneath its surface to understand what is truly happening. If you enjoy calm, deep and immersive space documentaries, consider liking the video and subscribing. Far from the planets, far from the dust that circles in slow bands round the Sun, the star rests in open space as a steady source of light, heat and motion. It stands at the centre of the solar system, holding the planets, moons, comets, and small fragments of rock in long paths shaped by gravity. Around it lies no hard border, no wall, no fixed edge, but a gradual spread of influence that reaches outward through darkness. The Sun appears from this outer view not as a flat disk in a daytime sky, but as a star among stars, though much nearer than any other. Its brightness overwhelms nearby space, and its presence defines the entire local system. In this distant setting, the Sun can be understood first as a sphere of hot plasma. Plasma is gas heated so strongly that its atoms no longer hold tightly to all of their electrons. The result is matter that responds not only to heat and motion, but also to magnetic fields. This state is common in stars. It is less familiar in daily life on Earth, where matter is more often seen as solid liquid or ordinary gas. Yet in the broader universe, plasma is widespread. The Sun belongs fully to that wider pattern. It is not a burning object in the sense of wood or coal. It does not consume chemical fuel. Its energy comes from nuclear fusion in its deep interior, where light atomic nuclei join and release energy. From far away, however, that internal process remains hidden. What can be seen first is the result a star radiating continuously into space. Its light spreads in all directions. Every second, an immense flow of energy leaves the Sun and crosses the solar system. A very small fraction reaches Earth, yet even that small share drives weather, warms oceans, lifts water into clouds, and supports life through photosynthesis. The Sun is therefore both distant and intimate. It remains nearly 150 million kilometers from Earth on average, and still it governs the daily rhythm of light and dark. From the outer perspective, this contrast becomes clearer. A body that seems ordinary in the daytime sky is revealed as the dominant object of the local cosmic region. The Sun is also large beyond ordinary comparison. Its diameter is about 1,390,000 kilometers wide, enough to place more than 100 Earths side by side across it. Its mass contains almost all of the mass of the solar system. The planets move as they do because the Sun's gravity shapes their paths. Even the most remote objects that still belong to the solar system remain in some degree under its rule. From a great distance, this gravitational order appears calm and silent. Nothing suggests hurry. The planets continue in their courses. The light continues outward. The system holds together. Yet the Sun is not still in every sense. It rotates. It changes. Its surface and atmosphere are shaped by strong magnetic fields. Its energy output varies slightly over time. Its outer layers release streams of particles into space. These changes matter because the Sun is not only a source of light, it is also an active star. The space around it is not empty in the simple sense. It is filled with radiation, magnetic structure, and particles moving outward. Even before attention turns to any specific solar event, the broader truth is already present. The solar system exists inside the living reach of a star. This wider setting also helps explain why a feature such as a giant hole in the Sun can be misleading if taken too literally. The Sun does not open like a shell, and no empty cavity appears in the solid sense that the word hole may suggest. From far away, observers often use familiar words to name unfamiliar patterns. In solar science, some regions appear darker in certain forms of light because they are less dense or less bright than their surroundings. The term gives shape to observation, but the actual object belongs to stellar physics, not to ordinary landscape. Before moving closer, it is enough to understand that the Sun's visible appearance changes because its atmosphere and magnetic structure change. Darkness, brightness, motion, and release all depend on physical conditions in hot plasma rather than on cracks or gaps in solid material. Seen from the outside, the Sun also belongs to a larger stellar family. It is a G-type main sequence star middle-aged by stellar standards, with an age of about 4.5 billion years. It is not the largest star, nor the hottest, nor the most violent known. Many stars are brighter, heavier, and shorter lived. Many smaller stars burn more slowly and may endure much longer. Yet for Earth, comparison has limited importance. This particular star defines the local environment completely. Its ordinary behavior matters more to life on Earth than the extreme behavior of distant stars ever could. The darkness around the Sun in space is not emptiness in the absolute sense. It contains scattered particles, magnetic fields, and the faint presence of interplanetary dust. Light from the Sun falls across this sparse material and continues outward. The farther the distance, the more the Sun resembles a bright centre in a vast dim field. Still, its influence does not end where its light seems smaller. Gravity continues, outflow continues, magnetic effects continue. The Sun shapes a domain much larger than the visible sphere itself. From this outermost starting point, the star can be held in mind as both object and environment. It is an object because it has structure, mass, temperature, and rotation. It is an environment because it creates conditions far beyond its bright face. Space near Earth is partly solar weather. The paths of spacecraft, the behavior of planetary magnetic fields, and the arrival of high-speed particles all depend in some measure on what the Sun is doing. The star at the center is not merely shining. It is continuously extending itself into surrounding space. Nothing in this broad outer view requires urgency. The Sun remains what it has long been, a stable star with changing outer activity. Its power is constant in the large sense and variable in the local sense. It warms, illuminates, pulls, and releases. In open space, surrounded by the dark quiet of the solar system, it appears serene from a distance. Yet within that serenity lies motion without pause, and from that motion the rest of the solar system receives both order and change. Beyond the bright sphere of the Sun, its reach continues into a region that has no simple shape and no visible wall. This broad region is called the heliosphere. The word refers to the immense bubble formed by the Sun's outward flow of particles and magnetic influence as it presses into the surrounding interstellar medium. The interstellar medium is the thin gas and dust that exists between the stars of the Milky Way. The heliosphere is therefore not the Sun itself, and not the empty dark beyond it, but the great zone where the Sun's influence dominates over the local material of the galaxy. It is large beyond ordinary imagination, extending far past the orbit of Pluto, and continuing outward, until the pressure of the solar outflow can no longer hold back the matter that lies between the stars. In this far domain, the Sun is no longer understood mainly through visible light. Light leaves the Sun and races ahead without pause, but the heliosphere is formed by slower material, by charged particles that stream outward and carry magnetic fields with them. This outward stream does not fill space like water in a closed vessel. It expands through already existing space thinning as it goes, yet remaining strong enough across immense distance to carve out a region shaped by solar conditions. The result is a vast and shifting enclosure, not rigid, not smooth, and not perfectly round. The Sun moves through the galaxy, and the interstellar medium presses back. Because of this, the heliosphere is thought to have a somewhat rounded front and a longer trailing shape behind, though the exact form remains difficult to define in full detail. The scale of this region helps place every inner solar event into context. A change at the Sun does not remain near the Sun alone. Solar material moves outward through the heliosphere, carrying signs of what happened closer in. Some changes weaken with distance. Some blend into the background flow. Some move as disturbances, compressions, or fast streams that alter conditions far from their origin. The heliosphere is therefore the great field through which solar behavior becomes solar environment. It is the Sun expressed not as surface brightness, but as spatial influence over a vast surrounding volume. Within this domain, the density of matter is very low. Even so, the total effect is not small. The particles moving through the heliosphere shape magnetic conditions, affect the movement of cosmic rays, and create the broad space weather environment through which planets travel. Cosmic rays are high-energy particles that come largely from beyond the solar system, often from violent astrophysical events elsewhere in the galaxy. The heliosphere helps reduce some of their intensity near the inner planets by acting as a kind of magnetic and particle shield. This shielding is not perfect, and it changes with solar activity. Yet the large principle is clear. The Sun does not simply send light into a passive void. It maintains a dynamic region that filters and modifies the surrounding galactic environment. The outer boundary of the heliosphere is not a sharp line like the edge of a planet's atmosphere drawn on a diagram. It is a transition zone. One important part of this transition is the termination shock, where the outward solar wind slows from faster than the local speed of pressure waves to slower than that speed. Farther out lies the heliopause, generally understood as the boundary where the outward pressure of solar material balances the inward pressure of the interstellar medium. Beyond that is interstellar space, though. Even there, the story is not one of absolute separation. Magnetic fields interact. Particles cross. The transition is physical but not simple. The Voyagers, the long-travelling spacecraft launched in the 20th century, have provided direct measurements from the far edge of this region, and have shown that the boundary is real structured and more complex than earlier models suggested. From the perspective of the Sun, the heliosphere is its far breadth. From the perspective of Earth, it is the larger house within which the planet moves. Earth does not orbit in untouched space. It orbits inside this solar domain, immersed in conditions created by the Sun and modified by distance. Even the planets that seem remote from the Sun still lie within this common envelope of solar influence. The heliosphere joins them in one broad environmental system. It does not make all places within it the same. Conditions vary greatly from the inner solar system to the outer reaches. Still, the common source remains present everywhere within the boundary. Its size also means that time matters differently there. Light travels quickly across the solar system, particles do not. A signal in light from the Sun reaches Earth in about 8 minutes. The movement of solar wind structures across much larger distances takes days, weeks, months, or longer, depending on the speed and the distance involved. In the outer heliosphere, the Sun is still present, but often as a delayed physical history. Material there may carry the mark of earlier solar conditions, stretched and altered by the long journey outward. This gives the heliosphere a layered character in time as well as space. What exists far from the Sun is connected to events closer in, but not in the same moment. The heliosphere is also filled with structure rather than uniform flow. The Sun rotates, and because of this rotation the magnetic field carried outward does not remain straight. It twists into a spiral pattern known as the Parker spiral, named after the physicist Eugene Parker, who helped explain the solar wind theoretically. This means the heliosphere contains vast curved magnetic structure carried by the flowing plasma. Fast and slow streams can interact. Regions of compression can form where one part of the flow catches up with another. Shocks and disturbances can travel outward. Yet all of this remains at this scale part of the outer domain rather than of the Sun's visible body. The heliosphere is the Sun made spacious, diffuse and extended across billions of kilometers. In this immense region, the idea of a giant hole in the Sun has not yet become a local feature. At this distance, what matters first is that any opening in the Sun's outer magnetic structure can matter, because the Sun is already connected to far space through an enormous outward system. A local change on the Sun can feed into a domain that extends far beyond the star itself. That possibility rests on the existence of the heliosphere. Without this broad solar bubble, solar activity would still occur, but it would not define such a large environment around the Sun. The heliosphere, therefore, belongs to the outermost region of the subject. It is the Sun's most distant continuous expression, the widest sphere of solar influence before interstellar conditions take over. It is large, faint-changing, and mostly invisible to human senses, yet it is one of the central realities of the solar system. Every planet, every spacecraft that remains inside it, and every stream of solar particles moving through interplanetary space belongs to this larger structure first. In the dark between the stars, the Sun has made a place around itself, and that place endures as the broadest outer region of the story. Within the heliosphere, the space between the Sun and Earth is not still. It is filled with a continuous outward movement of solar material known as the solar wind. This wind is not wind in the earthly sense. It is not air passing over land or sea. It is a flow of plasma made mostly of electrons and protons, with a smaller amount of heavier charged particles. It leaves the Sun's outer atmosphere and spreads into interplanetary space, carrying energy, momentum and magnetic structure with it. By the time it passes the orbit of Earth, it is thin beyond ordinary human intuition, yet it remains physically important, because even a sparse flow can shape magnetic conditions and influence planetary space environments when it extends across such enormous distances. The solar wind fills the inner solar system as a normal condition rather than a rare event. It is present in quiet times as well as active times. Space between the Sun and Earth is therefore not empty in the simple sense. It is occupied by this steady outward stream, sometimes slower, sometimes faster, sometimes smoother, sometimes disturbed. The flow expands as it travels, and as it expands, its density falls. Even so, it remains connected to the Sun by origin and by magnetic structure. The Sun does not merely shine across space. It also releases part of its outer material into that space, and the solar wind is the ordinary form of that release. Near Earth's orbit, the speed of the solar wind often ranges from about 300 to 800 kilometers per second, though exact values vary with solar conditions and source regions on the Sun. The slower wind and the faster wind are not simply the same stream moving at different rates by chance. Observations show that they often come from different magnetic and atmospheric conditions on the Sun. The slower wind is commonly more variable and more difficult to trace to one simple source. The faster wind is often linked to coronal holes regions where magnetic field lines open more directly into space. At this stage, however, the important point is only that interplanetary space contains more than one kind of solar flow. The region between the Sun and Earth is shaped by differences in speed density and magnetic pattern, carried outward from the star, As the solar wind moves away from the Sun, it carries the solar magnetic field with it. Because the Sun rotates, this carried field does not point straight outward in a fixed radial pattern. Instead, it forms a curved spiral through interplanetary space. This large-scale magnetic shape gives the solar wind structure over vast distance. Earth travels through that structured flow as it orbits the Sun. The planet therefore encounters not only moving particles, but also changing magnetic conditions embedded within them. The solar wind is both matter and field together joined by the behavior of plasma. This is one reason why space weather cannot be described only by counting particles. Direction, speed, compression, and magnetic orientation all matter. The journey from the Sun to Earth takes time. Light from the Sun arrives in a little more than 8 minutes, but solar wind takes much longer. Depending on its speed, the flow may take around 2 to 4 days to travel from the Sun to Earth. This difference creates a layered awareness of the Sun. Human eyes and cameras see the Sun almost as it is in the present, with only a short delay. Instruments that measure the arrival of solar wind near Earth detect the later physical passage of material that left the Sun days before. The space between Sun and Earth therefore acts as a corridor of delayed consequence. A condition observed at the Sun may later appear in particle measurements near Earth, altered by travel expansion and interaction along the way. That interaction matters. The solar wind does not move through interplanetary space as a perfectly smooth sheet. Faster streams can catch up with slower streams ahead of them. When this happens, the plasma can become compressed. Regions of higher density and stronger magnetic field may form where flows interact. These broad interaction regions can travel outward through space and shape conditions near planetary orbits. They are part of the ordinary texture of interplanetary space. The route from Sun to Earth is not a simple empty line crossed by isolated bursts. It is a dynamic medium in which solar outflow can gather stretch and rearrange itself over distance. Earth moves through this medium continuously. Its orbital motion means that it does not remain under one fixed stream from the Sun. At the same time, the Sun's rotation brings different source regions into positions from which their outflow can spread through the inner solar system. As a result, the space around Earth changes over days and weeks, even when no dramatic solar eruption occurs. Instruments on spacecraft detect these shifts as changes in speed, density, temperature, and magnetic field. The solar wind is thus both background and event. It forms the usual condition of near-Earth space, yet its variations can still matter greatly. The particles in the solar wind are hot, but hot in space does not mean hot in the way a person near a fire feels heat. In a very thin plasma, temperature reflects the average energy of particles rather than the dense transfer of heat through constant contact. The solar wind can therefore have particles with high energies, while still being too sparse to warm an object in the ordinary human sense. What it does instead is interact electrically and magnetically with planetary environments, spacecraft surfaces, and the larger magnetic systems of the heliosphere. Its importance lies in these interactions rather than in direct warmth. The composition of the solar wind also carries information about the Sun. Because the particles come from the solar atmosphere, their charged states and elemental abundances can help scientists infer the conditions in the regions from which they escaped. In this way, the space between Sun and Earth becomes not only a path of transport but also a moving record. The solar wind arriving near Earth contains clues about temperature, magnetic connection, and source environment at the Sun. Those clues are not always simple to interpret. Different source regions can produce overlapping signals, and conditions can change during the journey. Even so, interplanetary space preserves part of the Sun's outer history in motion. This region between Sun and Earth is therefore best understood as a living extension of the Sun rather than a neutral gap. It is broad, sparse, structured, and active. It carries ordinary solar outflow in a continuous stream, along with variations that arise from the changing outer atmosphere of the star. By the time solar material reaches Earth's orbit, it has travelled far from its source, yet it still belongs to the Sun in composition, motion, and magnetic character. The space between the two bodies is not a silence between events. It is the place where solar activity becomes transit, where the star's influence moves outward in measurable form, and where the flowing matter of the Sun passes through the inner solar system as an enduring presence. Earth moves around the Sun within this continuous solar flow, not outside it. The planet circles at an average distance of about 150 million kilometers, following an orbital path that remains well inside the inner heliosphere. Along that path, Earth does not travel through a fixed and quiet emptiness. It passes through a changing stream of solar plasma and magnetic structure, and it does so without pause. The planet's place in the solar system is therefore not only a matter of distance from the Sun, it is also a matter of immersion within a wider solar environment that changes from day to day and from season to season in subtle but measurable ways. From this regional view, Earth appears as a small world embedded in a broad outward current. The solar wind reaches Earth after crossing interplanetary space, carrying with it both particles and magnetic fields from the Sun's outer atmosphere. Earth is not large enough to stop that flow directly with its solid body alone, nor is the atmosphere its first line of contact. Long before solar particles approach the lower atmosphere, they encounter Earth's magnetic field. That field creates a surrounding magnetic region called the magnetosphere. The magnetosphere is not a rigid shell. It is a shifting cavity formed where Earth's magnetic field stands against the pressure of the solar wind. Its shape depends strongly on the solar flow that surrounds it. On the side facing the Sun, it is compressed. On the night side, it stretches far outward into a long magnetic tail. This means that Earth's immediate space environment is partly made by the meeting between planetary magnetism and solar outflow. The planet carries its own magnetic structure generated deep within by motions in its liquid outer core, yet that structure is continuously pressed and reshaped by conditions arriving from the Sun. A stronger or faster solar wind can push the sunward boundary of the magnetosphere inward. A quieter flow allows it to expand somewhat outward. The size and form of this magnetic region are therefore not fixed. Earth travels inside a moving negotiation between solar pressure and planetary resistance. The atmosphere lies farther in below this magnetic interaction zone, and from this outer regional perspective it remains sheltered most of the time. The magnetic field diverts much of the incoming charged flow around the planet, rather than allowing it to strike the atmosphere directly over the whole globe. Some charged particles do enter more easily near the polar regions, where magnetic field lines guide them downward into the upper atmosphere. There they can contribute to auroras, the luminous displays seen near high latitudes. These lights are visible signs that Earth's place in the solar wind is active rather than passive. Even in ordinary conditions, the planet does not merely receive sunlight. It also encounters streams of charged matter that meet its magnetic field and sometimes reach the atmospheric edge. This larger setting helps explain why solar weather matters without making Earth seem fragile in a simple sense. Most of the time, Earth remains protected by layers of physical response. Its magnetic field and atmosphere together provide powerful shielding. Life at the surface is not directly exposed to the solar wind as open space is. Yet the protective systems are themselves dynamic. Satellites move through the outer regions where solar effects are stronger. Radio communication can be disturbed when the upper atmosphere changes. Electric currents can be induced in long conductors on the ground, when geomagnetic conditions become disturbed. Earth's place in the solar flow is therefore secure in the broad biological sense, but sensitive in technological and geophysical ways. The planet also moves while rotating. Every 24 hours, Earth turns once on its axis, and over the course of a year it completes one orbit around the Sun. These motions matter because no single side of Earth permanently faces the solar wind in a fixed way over long times. The day side is always the side toward the Sun at a given moment, but that side shifts across the globe as Earth rotates. Meanwhile, the orbital path carries Earth through changing sectors of interplanetary space. The solar wind itself varies because the Sun rotates and presents different source regions to the directions along which its outflow spreads. Earth, therefore, encounters a solar environment that changes through a combination of solar variation and planetary motion. The changing relationship is rhythmic yet never perfectly repeated. Spacecraft near Earth help reveal this surrounding condition. Some orbit the planet. Some sit farther upstream near the region where incoming solar wind can be measured before it reaches Earth's magnetosphere. These observations show that Earth is not isolated from the wider heliosphere. Instruments record changes in particle density, speed, and magnetic direction. They detect shocks, fast streams, and quieter intervals. They show that Earth's space environment is local in one sense and solar in another. The conditions near the planet are shaped at once by Earth's own magnetic field and by whatever the Sun has recently sent outward across interplanetary space. This region can be imagined as a place of meeting rather than a place of separation. The Sun and Earth do not touch, and the distance between them remains immense on human scales. Even so, the physical relation is immediate in effect. Earth resides within the Sun's outer influence and responds to it constantly. The solar wind is not an occasional visitor. It is the normal surrounding medium of the planet's outer space environment. Earth's magnetic field, in turn, does not merely exist in isolation. It works within that medium, shaping and being shaped by the encounter from this outer to inner path. Earth is therefore best understood first as a planet living inside solar conditions, before attention narrows to the instruments that watch the Sun itself. The important fact at this stage is not the detail of one observed solar feature, but the planetary setting that makes such a feature relevant. If the Sun releases a faster stream of plasma, Earth occupies a place where that stream can matter. If magnetic conditions in interplanetary space change, Earth has a magnetic boundary that will respond. The connection is not mysterious. It is physical, steady, and measurable. In the sunlight of the day, Earth seems chiefly warmed by radiation. In surrounding space, however, it also exists within an invisible flow of particles and magnetic structure that comes continuously from the star it orbits. The planet's place is not beyond that flow, but within it. Its sky's magnetic field, upper atmosphere, and orbital surroundings all belong to a larger solar environment. Earth remains a distinct world with its own geology, water, air, and life. Yet from this region of the story, it is above all a small magnetized planet traveling through the extended breadth of the Sun. From Earth's orbital region, attention turns inward toward the ways the Sun is watched from afar. The star is too bright, too hot, and too active to be understood by ordinary sight alone. Its visible light shows only part of its nature. Much of what matters in solar science appears in forms of radiation that human eyes cannot detect, including ultraviolet light, extreme ultraviolet light, and X-rays. To study the changing outer atmosphere of the Sun, scientists rely on instruments carried above Earth's atmosphere where these signals can be observed clearly. In this region of the subject, the focus is not yet on the Sun's visible surface or its deeper layers, but on the distant methods by which its broad outer patterns are recorded and followed. Earth's atmosphere is protective, yet it blocks much of the radiation that solar scientists need to measure. This is one reason why solar observatories are placed in space. Spacecraft can maintain a nearly continuous view of the Sun without the interruption of night weather or atmospheric absorption. From these remote platforms, the Sun is not merely a bright disk, but a structured object whose outer atmosphere glows differently at different temperatures and wavelengths. Instruments select narrow bands of light so that regions of hotter or cooler plasma can be distinguished. A dark region in one type of solar image may not be dark in visible light. It may instead be a place where the outer atmosphere is thinner or emitting less strongly at the temperature being observed. One important group of observatories has been built specifically to monitor the Sun's broad atmosphere and changing activity over long periods. Among the best known is the Solar Dynamics Observatory, launched by NASA to provide frequent detailed images of the Sun in many wavelengths. It watches the full disk of the Sun continuously and records features that change over minutes, hours, and days. Its instruments reveal the visible surface magnetic structure and outer atmosphere in different ways. From such observations, scientists can identify active regions, eruptions, filaments, bright loops, and coronal holes. A coronal hole is a region in the Sun's outer atmosphere where the plasma is less dense and the magnetic field opens more freely into space. In images that capture the corona at certain wavelengths, these regions appear darker than their surroundings. Another important mission has been the Solar and Heliospheric Observatory, a joint project of NASA and ESA. Operating for many years, it has watched the Sun from a stable location where the gravitational pull of Earth and Sun allows a spacecraft to remain in a useful observing position. From there, it has monitored the solar disk, the extended corona, and the stream of solar material moving outward. It has helped build the long record that allows solar features to be placed in context rather than seen as isolated moments. This continuity matters because many solar patterns take days to rotate across the visible disk, and some larger cycles unfold over years. A single image can be striking, but a sustained record is what allows science to distinguish ordinary structure from unusual change. Observing the Sun from afar also requires interpretation. The Sun's atmosphere cannot be touched directly by instruments, in the same way that air near Earth can be sampled by a passing aircraft. Most solar observations depend on light. Scientists infer temperature, motion density, and magnetic behavior by analyzing how plasma emits and absorbs radiation. Different wavelengths correspond to different temperature ranges and different conditions in the solar atmosphere. The resulting images are often shown in colors chosen for clarity rather than colors the eye would naturally see. These colors are useful maps, not literal portraits. They help identify structures that would otherwise remain hidden in invisible radiation. This distance between observation and interpretation is especially important when a large dark region is seen on the Sun. To a general audience, the image may suggest an opening a wound or a missing piece. To solar scientists, the darker appearance is a sign of specific atmospheric conditions. The region is not empty space seen through the Sun. It is part of the corona, the Sun's hot outer atmosphere viewed in a wavelength, where that part emits less strongly because its plasma is cooler in that particular observational sense or less dense than nearby regions. Observations indicate that such areas are often linked to open magnetic field lines and to faster solar wind streams. The language of observation must therefore be handled with care. The image is real, but the meaning of the image belongs to physics rather than to simple visual analogy. Remote solar watching also depends on position. Some spacecraft view the Sun from the general direction of Earth. Others have travelled closer to the Sun or to different orbital positions, adding new perspectives. The Parker Solar Probe, for example, moves through the Sun's outer environment at distances much closer than Earth's orbit, while the Solar Orbiter mission studies the Sun from varying angles and distances. These missions do not replace remote full-disk imaging. Instead, they add context. A spacecraft far away can show the whole face of the Sun at once. A spacecraft traveling closer can sample the surrounding environment and measure solar material before it has spread as widely through space. Together, these approaches strengthen understanding of how observed features relate to particle flow and magnetic structure. Forecasting also grows from this distant watchfulness. Space weather prediction begins with observation of the Sun's broad surface and atmospheric conditions. Scientists track which regions face Earth, how magnetic patterns are arranged, whether eruptions have occurred, and where coronal holes are positioned. Because the Sun rotates roughly once every 27 days as seen from Earth, large features can remain important over several days of observation. A coronal hole that rotates into an Earth-facing position can become a likely source of a faster solar wind stream that may later pass Earth. The delay between seeing the feature and receiving the stream gives forecasters time to estimate its possible arrival. This does not make predictions simple or exact. Solar wind propagation depends on speed surrounding flow and changing structure during transit. Still, the ability to watch from afar turns solar science into a practical observational discipline as well as a descriptive one. In this region, the Sun is encountered first through instruments data and patient interpretation. The star is too bright for casual seeing and too complex for a single kind of image to explain. Remote observatories therefore act as careful extensions of human sight. They reveal patterns that visible light alone conceals and allow large coronal features to be followed across time. Through them, the broad outer atmosphere of the Sun comes into view as a changing structured environment rather than a blank glow. The giant dark regions that draw public attention begin here not as objects of fear or mystery, but as features identified through steady watching. From a safe distance, their meaning gradually clarified by the long, quiet work of observation. The visible face of the Sun is called the photosphere. This is the layer that appears to human sight as the bright surface of the star, though it is not a solid crust or fixed skin. It is a region in the Sun's outer body where light can finally escape freely enough to travel outward into space. Below it, the Sun is too dense for light to move directly without countless interactions. Above it, the atmosphere grows thinner and more extended. The photosphere lies between these deeper and higher regions, and from a distance it presents the Sun as a bright, nearly uniform disk. In ordinary daylight on Earth, it is the part that overwhelms the sky. In solar science, it is the first clearly defined visible layer of the Sun's outer structure. This surface is not still. Even in quiet conditions, it is marked by a fine pattern called granulation. Granules are small cells of motion caused by convection, the rise of hotter plasma, and the sinking of cooler plasma. Convection is a way that heat is carried by moving material. In the photosphere, hotter plasma rises from below, releases energy, cools, and then descends again along the edges of these cells. Seen in high resolution, the surface has a softly mottled appearance, bright in the centers of granules and slightly darker at their boundaries. These patterns change over minutes. They are signs that the visible surface is part of a deeper moving system rather than a static shell. The temperature of the photosphere is lower than the temperature of the layers above it in the corona, which seems at first surprising. The visible surface is around 5,500 degrees Celsius, while the outer atmosphere can reach temperatures of more than 1 million degrees Celsius. This contrast has long been one of the central puzzles of solar physics. At the level of the photosphere, however, the key fact is not the later puzzle of coronal heating, but the immediate appearance of steady radiance. The photosphere is where the sun shines most strongly in visible light. It is the layer that defines the familiar brightness of the star. Its light is not pure white in any simple sense. It contains a wide spread of wavelengths, and this broad spectrum is what makes sunlight capable of warming surfaces, illuminating clouds, and supporting the chemistry of life on Earth. When passed through instruments, this light reveals dark absorption lines caused by different elements in the sun's outer layers, absorbing specific wavelengths. These lines allow scientists to identify chemical elements present in the solar atmosphere and to measure motion through shifts in wavelength. Even the apparently simple brightness of the sun's surface therefore contains detailed physical information. The photosphere is not only luminous, it is readable. Across most of its area, the photosphere appears comparatively calm when viewed at moderate scale. It is bright, broadly even, and continuous. This calm appearance matters because it provides the visual contrast against which more distinct features stand out. Dark sunspots, bright faculae, and the larger patterns of solar activity are recognized against this luminous background. Yet in a quieter view, before those features dominate, the photosphere can be understood as the sun's visible threshold. It is the layer from which the star's outward appearance begins. What lies below remains hidden from direct sight. What lies above is revealed more clearly in special wavelengths. The photosphere therefore acts as the familiar outer face of the sun without being its true outer limit. The edge of the solar disk seen from afar also tells part of this story. The sun appears slightly dimmer near its edge than at its centre, a phenomenon known as limb darkening. This happens because when looking toward the centre of the disk, observation reaches somewhat deeper into hotter layers. Near the edge, the line of sight passes through shallower, cooler layers. The effect is gentle but measurable. It reminds observers that even the visible disk has depth and structure. The sun does not present a flat painted circle. Its brightness changes subtly because the surface is a layer of glowing gas viewed through varying paths of sight. The photosphere also changes across the solar cycle. The sun follows an activity cycle of about 11 years during which the number of sunspots and active regions rises and falls. During quieter phases, the visible surface appears less marked by large magnetic disturbances. During more active phases, sunspots and bright magnetic features become more common. The total brightness of the sun changes only slightly across this cycle, yet the patterning of the photosphere changes more noticeably. This makes the visible surface both stable and variable at once. It remains the bright face of the sun through all phases, yet the details written across it shift with the star's magnetic rhythm. Although the photosphere is often called the sun's surface, the word surface must be used carefully. In everyday language, a surface is the boundary of a solid object. On the sun, the photosphere is instead the layer from which photons, particles of light, are able to escape into space with relative freedom. It is an optical boundary more than a material one. If a body could somehow move downward through it, there would be no landing on a hard plane. The plasma would simply grow denser and hotter. The visible surface is therefore real as an observational layer, but not as a solid edge. This distinction becomes important when thinking about dramatic descriptions of the sun. Reports of a giant dark area or a hole in the sun can create the impression that the visible surface has been torn open. The photosphere itself usually does not show such coronal holes as great missing black regions in ordinary visible light. Those features are mainly seen in the outer atmosphere in other wavelengths observed by spacecraft. The visible surface remains largely continuous beneath them. This means the sun's familiar bright face often appears calmer than the more dynamic and patchy atmosphere above it. The photosphere can host magnetic signs and darker spots, but the large coronal openings belong chiefly to higher layers. In this region of the story, the Sun is encountered as light made visible in its most familiar form. The photosphere is bright, granular, gently changing and rich with hidden information. It is the layer that gives the Sun its ordinary appearance, while quietly revealing the motions beneath. It does not yet display the full drama of the outer atmosphere, nor does it expose the deeper interior. Instead, it offers a steady threshold, luminous and restless, where the Sun becomes visible to distant observers as a radiant sphere rather than a hidden engine of plasma and magnetic fields. Across the bright field of the photosphere, certain regions appear darker, cooler, and more structured than their surroundings. These are sunspots, visible signs of concentrated magnetic activity at the Sun's surface. They do not remain fixed in place forever. They emerge, evolve, and fade over periods that can last from days to weeks. Their presence marks areas where the Sun's magnetic field becomes strong enough to alter the normal flow of heat from below. In these regions, energy rises less efficiently, and the surface temperature drops slightly compared to the surrounding photosphere. This difference in temperature makes them appear dark by contrast, even though they still emit significant light. A typical sunspot consists of two main parts. At its center lies the umbra, the darkest region where the magnetic field is strongest and most vertical. Surrounding it is the penumbra, a lighter filamented area, where the magnetic field spreads outward and becomes more inclined. The structure is not static. Fine strands of plasma move along magnetic pathways, forming patterns that change over time. The size of a sunspot can vary widely. Some are small and short-lived. Others can grow to many times the diameter of Earth before gradually dissolving back into the surrounding photosphere. Despite their changing shapes, they remain anchored to deeper magnetic processes that extend below the visible surface. Sunspots rarely appear alone. They often form in pairs or groups known as active regions. In such regions, magnetic field lines emerge from the solar interior loop, outward through the atmosphere and return below the surface. One part of the pair typically shows magnetic polarity opposite to the other, meaning the direction of the magnetic field is reversed between them. This arrangement reflects the complex and dynamic nature of the Sun's internal magnetic system. The field is generated by the motion of plasma in the convection zone beneath the photosphere. As that plasma moves, rotates, and twists, it shapes magnetic lines into loops and structures that can rise toward the surface. The number of sunspots changes over time in a regular pattern known as the solar cycle. Over a period of about 11 years, the Sun moves from a quieter phase with fewer sunspots to a more active phase with many. During the active phase, the photosphere becomes more marked by these dark regions and by associated bright areas called faculae. Faculae are regions of enhanced brightness that often surround sunspots or appear near the solar limb. They are linked to magnetic activity as well, though they appear brighter rather than darker. Together, sunspots and faculae trace the shifting magnetic landscape of the Sun's visible surface. The presence of strong magnetic fields in active regions affects not only the appearance of the photosphere, but also the behavior of the layers above it. Magnetic loops rising from sunspots can extend into the chromosphere and corona shaping arcs of glowing plasma that are visible in ultraviolet and X-ray images. These loops can trap hot plasma, guide its motion, and sometimes store energy that is later released in sudden events. At the level of the photosphere, however, the emphasis remains on the visible pattern of magnetic concentration. The deeper processes that generate these fields remain hidden from direct view, but their effects are clearly written across the surface in the form of sunspots and active regions. The motion of sunspots across the solar disk also reveals the rotation of the Sun. As the Sun turns, sunspots appear to move from one edge of the visible disk to the other over a period of about 2 weeks. This apparent motion reflects the rotation of the photosphere itself. However, the Sun does not rotate as a solid body. Different latitudes rotate at different rates, a phenomenon known as differential rotation. Near the equator, the surface completes a rotation in about 25 days. Near the poles, the rotation takes longer. This difference stretches and twists magnetic field lines over time, contributing to the complexity of the Sun's magnetic behavior. The life cycle of a sunspot provides insight into the balance between magnetic forces and convective motion. A sunspot forms when magnetic flux rises from below the photosphere and becomes concentrated at the surface. It grows as more magnetic material emerges, stabilizing the region against convective mixing. Over time, the surrounding plasma begins to erode the structure. Magnetic lines disperse, the temperature difference lessens, and the sunspot fades. This process reflects the dynamic equilibrium of the solar surface, where magnetic structure can briefly dominate before being reshaped by the ongoing flow of plasma. Observations indicate that sunspots are often associated with increased solar activity. Regions with strong magnetic fields can give rise to solar flares and other energetic events. However, not every sunspot produces such activity. The relationship between surface features and energetic events is complex. The arrangement, strength, and interaction of magnetic fields all play a role. At this stage, the visible surface provides clues rather than complete explanations. It shows where magnetic energy is concentrated, but it does not always reveal how that energy will evolve. From the perspective of a distant observer, sunspots add texture and variation to the Sun's otherwise bright face. They serve as markers of the star's magnetic life, indicating regions where deeper processes reach the surface. Their changing number over the solar cycle offers a measure of the Sun's broader rhythm. Their motion reveals rotation. Their structure hints at the interplay between plasma flow and magnetic control. In the quiet glow of the photosphere, these darker regions stand out as signs that the Sun is not uniform but layered with patterns shaped by forces that extend beneath and above the visible surface. In relation to the larger topic, sunspots and active regions form an important step between the calm appearance of the photosphere and the more extended features of the outer atmosphere. They represent the point where magnetic structure becomes clearly visible at the surface. The dark openings seen in coronal images are not the same as sunspots, yet both arise from the Sun's magnetic behavior. Understanding the visible surface and its magnetic markings provides a foundation for recognizing how more subtle or more extensive features appear in the layers above. The photosphere, marked by sunspots and active regions, remains a place of constant change beneath a steady glow. It is neither smooth nor chaotic, but structured by patterns that evolve with time. Each dark region, each bright patch, and each shifting boundary reflects the ongoing motion of plasma and magnetic field within the Sun. From this level, the star's surface begins to reveal the forces that shape its outer atmosphere, preparing the way for a closer look at the regions where those forces extend beyond the visible light into the hotter and more diffuse layers above. Above the visible surface of the Sun, in the hot outer atmosphere called the corona, some regions appear darker and more open than the glowing structures around them. These are coronal holes. The word hole is useful only as a description of appearance. It does not mean that part of the Sun is missing or torn away. It does not describe an opening through the star or an empty cavity in a solid body. A coronal hole is a region where the corona is thinner and less bright in certain wavelengths of light, especially in extreme ultraviolet and X-ray observations. The darkness comes from reduced emission, not from absence of the Sun itself. It is a feature of the outer atmosphere shaped by magnetic structure and plasma conditions. When viewed in images from solar observatories, a coronal hole can cover a very large area. Some are modest and short-lived, Others extend across a substantial fraction of the solar disk and remain visible for days or even longer as the sun rotates. Their boundaries are often irregular. They may spread in broad dark patches, sometimes with curved edges, sometimes with long elongated shapes. Against the brighter corona around them, these regions stand out clearly. This contrast is one reason public attention often turns toward them when images are released. A large dark region on the sun can seem dramatic at first glance, yet in scientific terms it is a known and recurring feature of solar behavior. The reason a coronal hole looks dark lies in the conditions of the plasma within it. The corona emits strongly in certain wavelengths when its plasma is hot and dense enough to do so. In a coronal hole, the plasma is generally less dense than in surrounding coronal regions, and this lower density means less light is emitted at the wavelengths commonly used to image the hot outer atmosphere. The region is still extremely hot by ordinary standards. It is not dark because it is cold in the human sense. It is dark because relative to neighbouring parts of the corona, it contains less emitting material along the line of sight. Coronal holes can appear near the poles of the sun or at lower latitudes. Polar coronal holes are often present during quieter phases of the solar cycle and can persist for long periods. Lower latitude holes, sometimes called equatorial coronal holes, when they extend closer to the sun's middle latitudes, are often more relevant to Earth because they are more likely to rotate into positions where their outward flowing solar wind can intersect Earth's orbit. Their shape and persistence vary. Some remain stable over several solar rotations, others change more quickly. Observations indicate that their evolution depends on the larger magnetic pattern of the sun at the time. This feature differs from a sunspot in both location and physical meaning. A sunspot belongs to the photosphere, the visible surface, where strong magnetic fields suppress convection and make a region cooler and darker than the surrounding surface. A coronal hole belongs to the corona far above the visible surface, where the atmosphere is hot, thin, and structured by magnetic fields that allow plasma to escape more easily into space. The two features can both appear dark in images, but they are not the same kind of structure. One marks concentrated magnetic activity at the visible surface. The other marks an open atmospheric region in the outer solar environment. The language used in public reporting can sometimes blur this difference. A giant hole in the sun is an attention-drawing phrase, but the science is calmer and more precise. The sun's bright surface remains present beneath the overlying atmospheric feature. Nothing has opened downward into the body of the star. What is seen is a large region of the corona that is less bright than the surrounding atmosphere in a chosen wavelength. The image is real. The darkness is real in the observational sense. But the meaning belongs to the behavior of hot plasma and magnetic fields rather than to the familiar geometry of broken surfaces and empty spaces. Coronal holes are important because they are associated with open magnetic field lines. In much of the corona, magnetic field lines form closed loops that arch upward and return to the sun. In a coronal hole, many field lines do not close back nearby in the same way. Instead, they extend outward into interplanetary space. This open configuration gives plasma a more direct path away from the sun, and for that reason coronal holes are known sources of faster solar wind. At this stage, the focus remains on the atmospheric feature itself, rather than on the full journey of the wind, but the connection is central to the identity of the region. A coronal hole is not only darker than its surroundings, it is also more outwardly connected to space. Its boundaries are not always sharp. In some images, the edge between bright corona and darker hole appears gradual with fine magnetic and plasma structures, creating a textured transition. The region may contain smaller bright points within it, and surrounding areas may shift as the solar magnetic field evolves. Scientists track these changes carefully because the size, position, and orientation of a coronal hole help indicate where faster streams of solar wind may emerge. Even so, the appearance alone does not tell the whole story. The actual speed and effect of the resulting wind depend on conditions that unfold over distance and time. A coronal hole is therefore both a visible atmospheric pattern and a sign of deeper magnetic arrangement. It belongs to the corona, yet it reflects magnetic roots anchored farther down. It appears dark, yet it is not empty. It is associated with outflow, yet it is not itself the moving stream through space. It is best understood as a region of the Sun's outer atmosphere where the usual bright, dense coronal structure gives way to a more open, thinner state. In images, that difference becomes visible as darkness. In physical terms, it becomes meaningful as connection. Seen in this way, the giant dark region on the Sun becomes less a spectacle than a quiet structural fact. It is a large atmospheric area where the corona emits less strongly, and where the magnetic architecture opens into space. The feature can be broad, persistent, and important for conditions in the heliosphere, but its presence is part of the normal range of solar behavior. It belongs to the outer atmosphere of a magnetically active star, and its darkness is the readable sign of how that atmosphere is arranged. Within the calm logic of solar physics, a coronal hole is not an alarm in itself. It is a window into the Sun's outer structure, visible only because the corona is not uniform, and because careful instruments can distinguish one kind of hot sparse region from another. The corona surrounds the Sun as its outer atmosphere, extending far above the visible surface into space. It is thin, structured, and extremely hot, with temperatures that commonly reach more than 1 million degrees Celsius. This is far hotter than the photosphere below, even though the photosphere is the bright layer that appears to be the Sun's surface. The corona is therefore one of the most unusual regions of the Sun. It is faint in visible light, difficult to see directly, except during a total solar eclipse or with specialized instruments, yet it contains some of the most revealing signs of solar activity. In this region, the Sun's atmosphere becomes sparse enough to stretch outward across great distances while still remaining shaped by intense magnetic control. In ordinary daylight, the corona is hidden by the overwhelming brightness of the photosphere. During a total solar eclipse, when the moon blocks the bright solar disk, the corona becomes visible as a pale, extended halo around the darkened Sun. Even then, what appears to the eye is only part of its full structure. Spacecraft observing in ultraviolet and X-ray wavelengths reveal a far more detailed corona full of loops, streamers, bright arcs, and darker open regions. These forms do not arise from solid surfaces or fixed weather layers like those of a planet. They're made of hot plasma guided by magnetic fields. The corona is therefore not shaped mainly by gravity in the simple, downward sense, nor by fluid motion alone. Its architecture is largely magnetic. This hot outer atmosphere is also remarkably thin. Density in the corona is far lower than density in the photosphere below. That thinness is one reason it emits less visible light and is hard to see without special conditions. Yet thinness does not mean insignificance. In plasma physics, a low-density region can still be highly active if its particles carry large energies and respond strongly to magnetic forces. The corona is a place where that principle becomes visible. It is sparse enough to be transparent in many ways, yet structured enough to show complex and changing forms across the whole solar disk and beyond its edge. One of the long-standing questions in solar physics concerns why the corona is so hot. Since the photosphere below is cooler, heat does not simply rise in the ordinary everyday sense. Observations indicate that energy generated deeper within the Sun is carried upward and somehow deposited in the outer atmosphere, but the detailed process remains an active area of study. Magnetic waves and small-scale magnetic reconnection are among the leading explanations. Reconnection refers to the rearrangement of magnetic field lines in plasma, allowing magnetic energy to be converted into heat and motion. The general conclusion is strong even if some details remain uncertain. The corona is heated by processes linked to the Sun's magnetic field and the movement of plasma beneath and within it. The corona is not the same everywhere. Some regions glow more brightly because plasma is trapped in dense magnetic loops and heated to temperatures that emit strongly in the wavelengths being observed. Other regions are dimmer because the plasma is thinner, more open, or at a temperature that contributes less to a given image. This is why the corona often appears patchy and uneven rather than smooth. It is an atmosphere, but not one arranged in simple horizontal layers like the atmosphere of Earth. Its structure follows magnetic pathways. Bright arches trace closed loops. Long streamers extend outward above larger magnetic patterns. Coronal holes appear where the atmosphere is more open and less dense. The shape of the corona changes with the solar cycle. During quieter phases, it often appears more regular with broad streamers and persistent polar holes. During more active phases, it becomes more complex with many bright, active regions, tangled loops and changing patterns across a wider range of latitudes. These large changes reflect the Sun's evolving global magnetic field. The corona is therefore a visible expression of the Sun's magnetic state on the largest atmospheric scale. It records both local structures and the broader organization of the star's outer magnetism. Although the corona extends smoothly outward in one sense, it does not have a clear upper boundary like the edge of a cloud. It gradually merges into the outward flow of solar material that becomes the solar wind. In this way, the corona is both atmosphere and source region. It is still part of the Sun, yet it is also the place where solar plasma begins to move into interplanetary space in a more continuous way. This makes it a transitional region between the star as an object and the heliosphere as an extended domain. The corona remains gravitationally tied to the Sun, but parts of it are already flowing outward along open magnetic routes. In coronal holes, this openness becomes especially important. The surrounding corona helps make that difference visible. Against a brighter and more structured background, the darker region stands out because it lacks some of the dense glowing loops seen elsewhere. The contrast reveals that the corona is not uniform in density, temperature, or magnetic shape. A coronal hole is meaningful only because it is part of this larger atmospheric setting. Without the corona around it, there would be no visible distinction to observe. The hole is not separate from the corona. It is one particular state of the corona. The corona also responds quickly to magnetic change. Loops can brighten, fade, or rearrange over hours. Large-scale structures can endure longer, but even these are not permanent. The atmosphere remains in motion, though not always through obvious bulk flow alone. Heat waves, magnetic tension, and plasma pressure all contribute to its behavior. Instruments watching in multiple wavelengths show that different parts of the corona may highlight different temperatures and structures at the same time. What appears simple in one image may contain layered complexity when viewed through another. In this region of the story, the Sun is no longer the bright disk of ordinary daylight. It is a star surrounded by a hot, faint, magnetically organized atmosphere that stretches into space. The corona is sparse yet energetic, difficult to see yet physically decisive. It is the layer in which large, dark openings become visible, where magnetic shape dominates atmospheric form, and where the Sun's outer environment begins to connect directly with interplanetary space. Its light is thin, its heat is immense, and its structure is written not in stone or cloud, but in the invisible order of magnetic fields, guiding hot plasma through the outermost atmosphere of the Sun. Within and around a coronal hole, the most important hidden structure is the magnetic field. The corona is made of plasma, and plasma responds strongly to magnetism. This means the shape of the solar atmosphere is not determined by gas pressure alone. It is guided, channeled, and constrained by invisible magnetic lines that thread through the sun's outer layers. In many parts of the corona, these lines form closed loops. They rise from one part of the surface arch through the hot atmosphere and return to the sun nearby. Such loops can trap hot plasma, hold it above the surface, and make bright coronal structures visible in ultraviolet images. In a coronal hole, by contrast, much of the magnetic field is open. The lines do not quickly bend back down into a nearby loop. They extend outward into space. The phrase open magnetic field does not mean that a line is cut or broken in the ordinary sense. A magnetic field line is a way of describing direction and structure in space. It marks the path along which magnetic influence is arranged. In a closed region, these paths curve back toward the sun and contain plasma in arching forms. In an open region, the paths continue outward far more directly, linking the corona to the wider heliosphere. This difference is central to the nature of a coronal hole. The hole appears dark partly because it contains less dense plasma, and that lower density is connected to the fact that the magnetic structure allows material to escape rather than remain gathered in many bright closed loops. These open pathways are rooted in the sun below, but in the corona they create an atmosphere that behaves differently from the brighter surrounding regions. A closed loop can hold plasma for longer times. It can be heated, filled, and made visible as a luminous coronal arc. An open path offers less confinement. Plasma can move outward along it, and the result is a region that looks more sparse in coronal images. The magnetic difference is therefore not a small detail hidden beneath appearance. It is the organizing cause of the appearance itself. The darkened region is visible because the invisible field within it is arranged in another way. The sun's magnetic field is not simple. It is generated by the movement of plasma inside the star, shaped by rotation, convection, and long-term solar cycles. At the surface and above it, this field becomes a vast changing pattern of loops, open channels, and large-scale polarity regions. Polarity refers to the directional character of the magnetic field. One region may be dominated by field lines directed outward from the sun, while another is dominated by field lines directed inward. Coronal holes are often associated with large unipolar regions, meaning one magnetic direction dominates over a wide area. This helps support a more open magnetic structure, extending upward into the corona and outward into space. The openness is not absolute in every fine detail. The corona is textured and dynamic. Small loops, bright points, and boundary structures may still appear within or near a coronal hole. The solar magnetic field is never a perfectly simple drawing, yet the broader pattern remains clear. Compared with neighbouring coronal regions, the hole is characterized by a greater presence of field lines that reach outward rather than closing nearby. This large-scale tendency is what matters most for the structure of the atmosphere and for the origin of faster solar wind from the region. These field lines are not visible directly to the human eye. They are inferred from measurements of the magnetic field at the photosphere and from the way plasma glows and moves in the atmosphere above. Scientists map the magnetic field at the visible surface, then use physical models to estimate how that field extends into the corona. They compare those models with ultraviolet and X-ray images of coronal structure. The match is not perfect in every detail because the corona is complex and changing, but the overall relation is well established. Bright loops commonly mark closed fields. Dark coronal holes commonly mark open fields. The importance of open magnetic pathways extends beyond the appearance of the sun. Along such pathways, the corona is more directly connected to interplanetary space. Matter and energy can move outward with less trapping. The magnetic field carried away by the solar wind also reflects this structure. As the Sun rotates, the outward extending open field becomes part of the spiral magnetic pattern carried through the heliosphere. In this way, the coronal hole is not only a local atmospheric feature, it is one visible place where the Sun's magnetic architecture opens into the larger solar system. At the boundaries between open and closed regions, the field can be especially complex. Their different magnetic domains meet. Small changes in the field can alter whether plasma is confined in loops or allowed to escape. These boundaries are areas of interest because they may influence how the solar wind is fed and how coronal structures evolve. Observations indicate that the edge of a coronal hole is often not smooth in magnetic terms. It can shift as the surface field changes, as small loops emerge or disappear, and as the large-scale solar field is rearranged over time. The hole's outline in an image is therefore the visible trace of a magnetic border that is active rather than fixed. The open magnetic structure also helps explain why a coronal hole can matter when it faces Earth. If the hole is positioned so that its open field and resulting outflow are directed into the region of space, Earth will soon occupy the faster solar wind from that area can later reach Earth's orbit. The key connection begins here in the magnetic geometry of the corona. The field does not merely decorate the atmosphere, it determines which regions are closed and bright and which are open and dark. It decides whether plasma is more likely to remain suspended above the Sun or to move outward into space. In this region of the story, the corona becomes readable through magnetism. What seems at first like a dark patch in a hot atmosphere turns out to be a map of invisible structure. The coronal hole is dark because it is open, and it is open because the magnetic field there follows paths that lead away from the Sun rather than arching back nearby. The atmosphere takes its form from those paths. Its brightness, density, and connection to space all depend on them. The Sun's outer layers are therefore not shaped mainly by visible matter alone, but by magnetic order written through that matter, guiding it into loops, borders, and outward channels that reach far beyond the bright body of the star. Along these open magnetic pathways, the matter of the corona does not remain confined. It moves outward as part of the solar wind. This matter is plasma, a state in which atoms are separated into charged particles, mainly protons and electrons, with a smaller fraction of heavier ions. In the corona, this plasma is extremely hot, yet also very sparse. Its behavior is governed not only by temperature and pressure, but by the magnetic field that shapes its motion. In a coronal hole where magnetic lines extend outward, plasma finds a more direct route into interplanetary space. The particles that make up this outward flow are not ejected in a single burst. The solar wind is a continuous stream. In regions of open magnetic field, this stream can become faster and more steady compared to other parts of the Sun. The plasma expands outward, and as it does, it carries with it the magnetic field embedded within it. This combination of particles and field is a defining feature of the solar wind. The plasma does not move independently of the magnetic structure. Instead, it flows along it, guided by it, and in turn stretches it outward across space. The process begins in the corona, where the temperature is high enough that particles have significant energy. Some of this energy is converted into outward motion. The exact mechanisms that provide this acceleration are still studied. Observations indicate that wave motion in the plasma and interactions within the magnetic field both play roles. These waves can transfer energy through the corona, pushing particles outward along open field lines. The result is not a sudden release, but a sustained flow, gradually accelerating as it moves away from the Sun. In a coronal hole, this outward movement becomes more efficient. The lack of closed magnetic loops means that fewer particles are trapped. Instead of circulating in arching structures, they are free to follow open paths. This leads to the formation of high-speed solar wind streams. These streams can reach speeds of several hundred kilometers per second or more as they travel through interplanetary space. Their properties differ from the slower wind that emerges from more complex magnetic regions. The faster wind is often less dense but more uniform in flow, reflecting its origin in open and extended magnetic fields. As the plasma leaves the corona, it continues to expand. The density decreases with distance, yet the total flow remains significant because it spreads across a vast volume of space. The particles carry energy, momentum, and magnetic influence far from the Sun. This outward movement is not simply a release of matter. It is part of a larger system in which the Sun continuously sheds material while maintaining its overall structure. The loss is small compared to the Sun's total mass, but it is constant over time. The composition of the solar wind provides insight into its origin. Measurements show that it consists mostly of hydrogen nuclei and electrons, with traces of helium and heavier elements. The charged states of these particles reflect the temperature and conditions of the corona where they formed. In this way, the solar wind acts as a moving sample of the Sun's outer atmosphere. Instruments near Earth and on spacecraft farther out can analyze these particles, offering indirect knowledge of the regions from which they escaped. The magnetic field carried with the plasma remains organized even as the wind expands. Because the Sun rotates, the outward flowing field forms a spiral pattern through space. This structure is not imposed after the fact. It arises naturally from the combination of radial outflow and rotational motion at the source. As plasma travels outward, it preserves the orientation of the magnetic field lines, which become stretched and curved. This embedded field influences how solar wind streams interact with one another and how they affect planetary environments. The transition from the corona to the solar wind is gradual rather than abrupt. There is no sharp boundary where the atmosphere ends and the wind begins. Instead, the corona thins and expands, and its plasma becomes the solar wind as it moves outward. In coronal holes, this transition is more direct. The open magnetic structure allows plasma to escape with fewer obstacles, linking the atmosphere to the heliosphere more clearly. This makes these regions important for understanding how the Sun's influence extends into space. The outward flow is not perfectly smooth. Variations in speed and density arise from changes in the Sun's magnetic structure and from interactions between different streams. Faster wind can overtake slower wind, creating regions of compression. These interactions can enhance magnetic effects and influence conditions far from the Sun. Even so, the origin of the faster streams remains tied to the open magnetic regions in the corona. The coronal hole serves as the starting point for these flows, even though their later behavior depends on processes that occur over great distances. From this perspective, the coronal hole is not merely a dark patch on the Sun. It is a gateway through which solar material moves outward more freely. The plasma that leaves through these regions becomes part of the larger solar wind, carrying with it information about the Sun's outer atmosphere and contributing to the conditions that planets experience. The connection between appearance and process becomes clear. The darkness seen in coronal images corresponds to a region where plasma density is lower and where magnetic structure allows matter to escape more directly. In this region of the story, the Sun's outer atmosphere is no longer only a place of structure and light. It is also a source of motion. Plasma flows outward, continuously guided by magnetic pathways that extend far into space. The coronal hole marks a region where this outward movement is especially direct and sustained. It reveals how the Sun's atmosphere is not confined to the star itself, but is part of a larger system, in which matter energy and magnetic fields move outward to shape the environment of the solar system. The outward flow of the solar wind does not begin as fast as it later becomes. Near the Sun, even in a coronal hole, the plasma starts within a region still strongly tied to the star's gravity. For that plasma to escape and continue outward across interplanetary space, it must gain enough energy to overcome the pull of the Sun and to keep accelerating through the expanding corona. This makes the question of acceleration central to solar physics. The existence of the solar wind is well established, and the association between coronal holes and faster streams is also well established. What remains less certain in full detail is exactly how the corona transfers enough energy and momentum to the plasma to produce the observed speeds. One part of the answer lies in heat. The corona is extraordinarily hot, far hotter than the visible surface below. In a hot gas or plasma, particles move with greater average energy. This thermal energy creates pressure, and pressure can drive expansion. The solar wind can therefore be understood in part as a natural result of a very hot outer atmosphere that cannot remain static. If the corona is heated strongly enough, its plasma expands outward, rather than resting quietly above the Sun. In this sense, the solar wind is partly the consequence of the corona's temperature. The Sun's outer atmosphere becomes too energetic to stay bound in a still and compact form. Yet heat alone does not appear to explain everything. Observations indicate that the faster wind from coronal holes often reaches speeds that suggest additional processes are at work. The acceleration is not merely a slow drifting outward under pressure. It seems to involve the transfer of energy through magnetic structure and wave motion as well. One important idea concerns Alpha-Venn waves. These are waves that travel along magnetic field lines in plasma somewhat like a disturbance moving along a stretched cord, though the comparison is only partial. In the Sun's atmosphere, such waves may carry energy upward from lower layers into the corona. As they travel and interact with the plasma, they may help push material outward and contribute to heating the surrounding region. The presence of open magnetic fields in coronal holes makes this possible pathway especially important. In a closed loop, energy carried by waves may remain more confined within an arching magnetic structure. In an open region, energy can be directed outward along field lines that connect more directly to space. This may help explain why the wind from coronal holes becomes faster and more sustained. The open field does not only allow particles to leave, it may also provide a route along which energy can travel and be deposited into the outflowing plasma. Observations support the role of waves, but the exact balance between wave-driven acceleration, thermal expansion, and other processes remains an area of active study. Another important process is magnetic reconnection. This occurs when magnetic field lines in plasma change their arrangement and release stored magnetic energy. In the corona, where magnetic fields are constantly stressed by motions below reconnection, can happen on many scales. Large reconnection events are associated with flares and eruptions, but smaller and more frequent events may also matter. Some scientists propose that numerous small reconnection events contribute to coronal heating and may also help feed or accelerate the solar wind. In and round coronal holes where open and closed fields can meet at boundaries, this kind of magnetic change may allow plasma to move from more confined regions into open pathways. The process is difficult to observe directly in every detail, yet the broader idea is physically plausible and supported by several lines of evidence. The acceleration of the solar wind is therefore not traced to one single cause with complete certainty. Instead, the current scientific picture points to a combination of effects. Thermal pressure from a very hot corona provides a basic outward drive. Magnetic waves likely carry energy through the atmosphere and transfer part of it to the plasma. Reconnection may release magnetic energy and open routes for material to escape. The relative importance of each process may vary from one region to another, and from one kind of solar wind to another. What is known firmly is that the Sun's outer atmosphere supplies both the matter and the energy needed for the flow. What remains uncertain is the exact partition of mechanisms that produces the final speed profile observed in space. As the plasma accelerates, it also changes its relationship to the Sun. Close to the Sun, gravity and local magnetic structure dominate strongly. Farther out, the flow becomes increasingly committed to outward motion. The solar wind passes through a critical point where it transitions from a more restrained outflow into a supersonic one, meaning it moves faster than the speed at which pressure disturbances can travel through the local plasma. Beyond that point, the wind continues outward as a true solar stream filling into planetary space. This transition is not visible to human eyes, but it is fundamental to how the solar wind becomes an enduring feature of the heliosphere rather than a temporary atmospheric motion. In coronal holes, the lower density of the corona may also aid the acceleration process. With fewer particles crowding the region, the available energy can be distributed differently than in denser closed-loop regions. This does not make the physics simple, but it helps explain why a darker and thinner coronal area can be associated with a faster outflow. The appearance of reduced brightness is linked to reduced density, and the reduced density is part of the physical environment in which faster wind can emerge. The dark feature in the image is therefore connected not only to structure but also to dynamics. This part of the story remains one of the quieter scientific frontiers. The main outlines are clear. The corona is hot enough to expand. Open magnetic fields provide outward routes. Waves and magnetic changes appear to add energy and momentum to the plasma. But solar physics still works to determine how these effects combine in detail, especially close to the Sun where direct measurement has long been difficult. Missions such as Parker Solar Probe have begun to sample the solar environment at much closer distances, offering new information about the wave's turbulence and magnetic structure present in the accelerating wind. These measurements continue to refine what is known. In this region, the solar wind becomes understandable, not just as matter in motion, but as matter receiving a sustained outward push from heat and magnetic energy. The Sun does not simply leak particles into space. It accelerates them through a complex atmospheric process rooted in plasma physics. Coronal holes matter because they reveal where that process can proceed along open pathways with unusual efficiency. The result is a faster stream that carries the signature of its origin outward into the heliosphere, linking the darkened appearance of the corona to the deeper and still partly unresolved question of how a star drives a continuous wind across space. Below the corona lies a thinner lower region, where the character of the Sun's atmosphere begins to change. This is not yet the bright visible surface, and not the million-degree outer atmosphere above, but the transition between them. In solar physics, this boundary region is often called the transition region, because over a very short distance the temperature rises sharply, the density falls, and the behavior of the plasma shifts from the conditions of the lower atmosphere toward those of the corona. It is not a broad calm layer with a simple uniform structure. It is narrow, irregular, and active, shaped by the movement of energy upward and by the magnetic field that threads through all of the Sun's outer regions. In this boundary zone, the plasma is denser than in the corona above, yet far less dense than at the visible surface below. Light from this region is not seen easily by ordinary human sight. It is studied mainly through ultraviolet observations made from space. These observations show that the transition region is bright in some wavelengths, flickering and fine-grained with many small structures tracing the places where energy moves through the lower atmosphere and into higher layers. The region is thin in geometric depth but not simple in physical behavior. It is one of the places where the Sun changes character most quickly. The most striking feature of this region is the rapid rise in temperature. Over a comparatively short vertical distance, the solar atmosphere passes from the cooler conditions of the chromosphere below into the much hotter conditions of the corona above. Observations show this temperature rise clearly, though the exact way energy is deposited through the region remains part of the broader coronal heating problem. The boundary does not act like a quiet dividing line between warm and hot layers. It behaves more like a narrow zone of exchange where energy carried upward through magnetic and plasma processes produces a steep thermal change. The atmosphere does not step upward in simple levels. It shifts through a small but highly dynamic interval. Magnetic fields are especially important here because they connect the denser lower atmosphere to the open and closed structures of the corona. Some magnetic lines arch into loops and return nearby. Others continue into larger structures or open outward through coronal holes. In the transition region, plasma responds to these magnetic paths while also remaining closely tied to local pressure and motion. The result is a textured and changing environment. Small jets, brightenings, and shifting threads of emission are often observed. These are not separate from the larger solar atmosphere. They are part of the way mass and energy are exchanged between lower and higher regions. This boundary is also a place where the flow of material can become more complex than a simple upward rise. Some plasma moves upward as heating increases. Some cools and falls back along magnetic structures. In closed-loop systems, this exchange can be continuous with matter cycling between denser lower layers and hotter upper layers. In open-field regions, the boundary may feed the outward-moving plasma that later becomes part of the solar wind. Even here, however, the distinction is not absolute. The Sun's atmosphere is not divided into isolated compartments. It is a connected system in which local conditions depend on magnetic geometry, heating rate, and the changing supply of plasma from below. Because the transition region is so thin and variable, it is difficult to describe with a single temperature or one stable height above the photosphere. Its location and behavior differ from place to place. Above active magnetic regions, it may be distorted by strong loops and concentrated heating. Above quieter regions, it may appear less bright, though still dynamic. Near coronal holes, its role is shaped by open magnetic structure and the reduced confinement of plasma overhead. This means the transition region is best understood not as a flat shell, but as a changing interface spread across the Sun with many local forms. Its importance lies in the fact that the corona cannot be understood without it. The hot outer atmosphere must receive energy and plasma through lower layers, and the transition region is one of the narrow places where that exchange becomes physically sharp. The coronal hole seen high above as a dark region in ultraviolet images depends in part on what happens here. The lower atmosphere supplies matter, the magnetic field arranges the available routes, and the transition region marks the passage into the much thinner and hotter corona. The dark opening above is not created here alone, but this boundary helps determine how the upper atmosphere is fed and how it differs from neighbouring regions. Instruments that observe ultraviolet emission lines allow scientists to measure motion in this region. Through Doppler shift, small changes in wavelength caused by movement toward or away from the observer. These measurements show that the transition region is full of motion. Some areas reveal upward flows, some downward flows, and some rapid local changes that reflect the restless interaction of heating and magnetic guidance. This has helped establish that the lower solar atmosphere is not a quiet foundation beneath an active corona. It is active in its own right, constantly passing energy and matter upward. The transition region also reveals how misleading ordinary visual language can be when applied to the Sun. There is no simple boundary where one could point and say that the surface ends and the atmosphere begins in the same way that land meets air on Earth. Instead, there are gradual and then very rapid changes in density, temperature, and emission, all within plasma that remains magnetically structured. The Sun is layered, but its layers interpenetrate through motion and field. The transition region makes this especially clear because it is a place of abrupt change without hard separation. In this region of the story, the Sun's atmosphere narrows into a delicate but powerful interface. Below it, the gas is denser and cooler. Above it, the corona spreads outward as a hot, sparse, magnetically shaped atmosphere. Between them lies a bright and shifting boundary, where energy passes upward, where temperature climbs rapidly, and where plasma begins to behave in ways that prepare it for life in the corona above. It is a thin region, almost modest in scale compared with the vast heliosphere or the broad corona, yet it carries great significance. Here the lower Sun gives way to the higher atmosphere, and the path inward continues through a boundary that is small in thickness, rich in motion, and central to the structure of the solar world. Below the transition region lies the chromosphere, a layer of the Sun's atmosphere that sits above the photosphere and below the hot outer corona. It is less familiar to ordinary sight than the bright visible surface, yet it is more substantial and more textured than the narrow boundary above it. The chromosphere is a region of rising complexity, where the Sun's atmosphere is still comparatively dense, where magnetic structure becomes increasingly visible, and where energy moving up from below begins to shape the dynamic forms that extend into the higher atmosphere. Its name comes from a word meaning colour, because during a total solar eclipse it can sometimes be seen briefly as a thin reddish rim around the darkened edge of the Sun. That reddish appearance comes mainly from hydrogen emission. Hydrogen, the most abundant element in the Sun, radiates strongly in a deep red wavelength under chromospheric conditions. Yet the chromosphere is not truly a uniform red shell surrounding the Sun like paint around a sphere. It is a changing, uneven layer filled with fine structures, local motions and magnetic features that rise and fall over short times. In ordinary daylight, it is hidden by the overwhelming brightness of the photosphere below. Only under special viewing conditions or through instruments designed to isolate particular wavelengths does the chromosphere reveal its own distinct character. The temperature in the chromosphere is generally higher than in the photosphere, though the increase is not smooth in every detail. Starting above the cooler visible surface, the temperature rises through the chromosphere as height increases, preparing the way for the much sharper rise in the transition region. This makes the chromosphere an important middle layer in the Sun's outer atmosphere. It is denser and cooler than the corona, but more active and structured than a simple intermediate shell might suggest. It is a region where the lower atmosphere begins to show the full influence of magnetic organization. One of the most common chromospheric features is the spicule. A spicule is a narrow jet of plasma that rises upward from the lower atmosphere, often lasting only a few minutes, before fading or falling back. Vast numbers of these fine jets appear across the Sun at any given time. They are slender, fast, and short-lived, and they may play an important role in transporting mass and energy upward into higher layers. Observations indicate that spicules are strongly guided by magnetic fields. They rise along magnetic pathways rather than in random directions, showing that even in this comparatively low atmospheric layer, the shape and motion of plasma are already tied closely to the Sun's magnetic structure. The chromosphere also contains filaments, plages, and network patterns. Filaments are cooler, denser ribbons of material suspended above the Sun by magnetic fields, often appearing dark against the bright solar disk in certain wavelengths. Plages are brighter chromospheric regions associated with magnetic activity, usually found above or near active regions on the photosphere. The magnetic network outlines larger-scale patterns linked to convective motions below, where magnetic fields are swept into lanes and concentrations by the turning cells of plasma, rising and sinking beneath the visible surface. These structures make the chromosphere look intricate and restless when seen through the right instruments. It is not smooth, it is not quiet. Yet its motion remains orderly in the sense that magnetism provides a framework for much of what appears there. The chromosphere is also the place where acoustic and magnetic disturbances from below continue upward and are transformed. Convection in the layers beneath the photosphere produces waves and motions that travel into the atmosphere. In the chromosphere, these disturbances can steepen into shocks, interact with magnetic fields, and deposit energy. The result is an atmosphere that is constantly stirred from below, while also constrained by magnetic tension from within. This helps explain why the chromosphere is dynamic on both small and large scales. It responds to the deeper churn of the sun, but it does not simply mirror it. The magnetic field alters how energy moves, how plasma rises, and how structures hold together. Compared with the corona above, the chromosphere is more crowded with matter. Plasma density remains much higher here than in the outer atmosphere, and this means that collisional processes still matter strongly. Particles interact more often. Radiative transfer, the movement of energy by light through matter, becomes complex. This makes the chromosphere one of the more difficult layers to model in full detail. Observations provide a rich picture of motion and emission, but the exact balance of heating processes is still not completely resolved. What is clear is that the chromosphere is not a passive layer waiting to be crossed. It is an active participant in the transport of energy and matter from the lower sun to the corona above. In regions that later support coronal holes overhead, the chromosphere still remains present as a structured lower atmosphere rather than a dark absence. The open magnetic pathways associated with coronal holes extend through it, but they do not remove it. Plasma continues to rise and move through this region, and the magnetic field continues to organize that motion. The difference lies in how those magnetic paths connect upward. In some regions, fields arch into closed loops. In others, they remain more open and continue into the corona and beyond. The chromosphere therefore helps anchor the magnetic geometry that will later appear higher up as bright loops or darker open holes in coronal images. This layer can be thought of as the sun's changing edge, not because it is the final outer limit, but because it marks the point where the familiar bright surface gives way to a visibly more atmospheric form. In the photosphere below, the sun appears as a luminous surface of granular light. In the chromosphere, that surface opens into jets, threads, and magnetic patterning. The atmosphere becomes more obviously vertical, more obviously structured by field, and more obviously in motion beyond the slow granulation of the visible surface. In this region of the story, the sun's lower atmosphere appears as a place of constant small scale, rising and falling, glowing and fading, guided by magnetism and fed by energy from below. The chromosphere is neither as bright as the photosphere nor as hot and diffuse as the corona. It is an intermediate realm with its own complexity, coloured by hydrogen light, rich with spicules and magnetic features, and essential to the movement of energy into the upper atmosphere. Here the path inward reaches the layer where the sun's atmosphere becomes visibly textured and dynamic, preparing the way for the final step below, where the visible surface yields to the moving plasma beneath. Below the bright photosphere, beneath the granules and the magnetic markings that appear on the visible surface, lies the upper convection zone. This is the outer part of the sun's interior, where energy is carried mainly by the movement of plasma rather than by radiation alone. It is not visible directly. No instrument sees into it in the ordinary sense. Yet its presence is known through theory, through measurements of motion at the surface, and through heliosismology, the study of waves moving through the Sun. In this hidden region, the plasma is hotter, denser, and under greater pressure than at the visible surface above. It moves continuously, rising and sinking in broad and small-scale patterns that help shape the magnetic life of the Sun. Convection is the transport of heat by moving material. In the Sun's outer interior, energy coming from deeper within cannot escape by radiation as easily as it can farther down. The plasma becomes opaque enough that light is scattered and absorbed again and again. Under these conditions, rising and sinking motion becomes an efficient way to move energy upward. Hotter plasma from below rises because it is slightly less dense than its surroundings. As it approaches higher layers, it releases energy, cools, and then sinks again. This overturning motion fills the convection zone with a restless pattern of circulation. Near the top, those motions appear at the surface as granulation and larger flow patterns. Below the surface, they extend downward into a broad hidden layer of moving plasma. The upper convection zone is not quiet or uniform. It contains flows on many scales. Some are small and short-lived, linked to the granules seen on the photosphere. Others are larger and longer-lived, forming supergranular patterns that help gather magnetic fields into network lanes at the surface. Beneath these visible expressions, the motion continues in complex ways that are difficult to picture in detail. The plasma is ionized, conductive, and rotating with the Sun. Because of this, its movement interacts strongly with magnetic fields. Motion can stretch, twist, and concentrate magnetic lines. Those lines in turn can resist or redirect motion. The upper convection zone is therefore both a thermal engine and a magnetic workshop. This interaction is central to the origin of the magnetic fields that later shape the photosphere, chromosphere, and corona. The Sun's magnetic field is generated by a dynamo process, meaning that moving electrically conducting plasma creates and maintains magnetic fields. Differential rotation, in which different latitudes rotate at different speeds, contributes to this process, as do convective motions that churn and twist the plasma. The deeper global dynamo of the Sun involves layers farther below as well, especially near the boundary between the convection zone and the radiative interior. But in the upper convection zone, those broader magnetic fields are worked on continuously by local motion. They are braided, concentrated, and sometimes brought upward toward the surface. Magnetic flux can rise through this region because magnetic structures may become buoyant. Buoyancy means that a region becomes effectively lighter than its surroundings and tends to rise. In the Sun, strong magnetic concentrations can reduce the local gas pressure enough to allow loops of magnetic field to move upward through the surrounding plasma. When such loops approach the photosphere and emerge through it, they can create active regions and sunspots. In this way, the visible magnetic patterns on the Sun are rooted in hidden motion below. The photosphere shows the results. The upper convection zone supplies much of the shaping process that makes those results possible. The relation to coronal holes is more indirect but still real. A coronal hole is an atmospheric region of open magnetic structure high above the surface. That open structure depends on the Sun's broader magnetic organization, and that organization cannot exist without the ongoing dynamo action and convective transport occurring beneath the surface. The upper convection zone does not produce a coronal hole by itself as one local event. Rather, it participates in the larger magnetic life of the Sun, from which surface fields, active regions, polar fields, and open atmospheric structures all ultimately emerge. The dark opening high in the corona therefore has roots in motions that remain hidden below the visible face of the star. Heliosismology has allowed scientists to infer much about this hidden region. The Sun vibrates with many waves that move through its interior and across its surface. By studying the frequencies and travel times of these waves, scientists can reconstruct properties of the solar interior, including rotation patterns and flow structures in the convection zone. This has shown that the outer layers of the Sun are not rotating as a solid body, and that convection interacts with rotation in ways that help sustain the magnetic cycle. Much remains difficult to resolve in detail, especially on smaller scales, but the overall picture is clear. The upper convection zone is a moving interior layer where heat transport and magnetic generation meet. Conditions there are very different from those at the surface. Temperatures rise rapidly with depth. Pressure becomes immense. Plasma remains fluid, not solid, despite the increase in density, because the temperatures are far too high for ordinary matter to take stable solid form. The Sun has no rocky crust beneath its glowing face. Instead, the apparent surface gives way to deeper and denser fluid layers, still in motion, still part of the star's continuous body. This is one of the great differences between a star and a planet. A planet may have an atmosphere above a solid or liquid surface. The Sun has atmosphere above atmosphere, and below the visible threshold it has deeper plasma, not land. In this innermost region of the present path, the story comes to rest in hidden motion rather than visible drama. The giant dark region seen from afar, the open corona, the faster solar wind, the magnetic pathways, the photospheric markings and the dynamic chromosphere all depend at some level on what happens here. Yet the upper convection zone itself remains unseen except through its effects. It is the buried source of much of the Sun's changing outer behavior, a vast layer of rising and sinking plasma, carrying heat upward and shaping magnetic fields that later appear above. The path from outer space to inner source ends here, not at a hard center, but at a hidden zone of motion beneath the light, where the Sun's visible calm is supported by an unending internal churn. In the end, the Sun remains where it has always been, a star suspended in quiet darkness, sending light heat particles and magnetic influence outward through the solar system. From the far edge of its influence to the hidden churn below its visible surface, each region belongs to one continuous body of plasma in motion. The heliosphere spreads wide into interstellar space. The solar wind crosses the long distance to Earth. The corona glows thin and hot above the bright surface. A dark coronal hole opens not as absence, but as a sign that the atmosphere there is sparse and magnetically connected to space. Beneath that, the lower atmosphere stirs with rising jets and changing light. Below the surface, convection moves steadily in deep patterns that shape the magnetic fields above. Nothing in this chain stands alone. The dark region seen in solar images is linked to open magnetic structure. The open magnetic structure is linked to the outward movement of plasma. The outward movement of plasma is linked to the heating and acceleration of the corona. The corona is linked to the lower atmospheric layers that feed it, and those layers are linked in turn to the hidden motions below the visible face of the Sun. What appears at first as a single striking feature becomes, when followed inward carefully, part of a larger and calmer order. Earth continues in its orbit within that order, moving through the Sun's extended environment, while remaining sheltered by its own magnetic field and atmosphere. The connection is real, physical, and ongoing. The Sun does not need spectacle to matter. Its ordinary activity is enough to shape the space around every planet near it. In the slow rhythm of stellar motion, the great dark opening in the Sun's atmosphere becomes simply one readable part of a living star, vast, bright, and never still.